So welcome back. As promised, I would like to provide some more details, especially linked to an application in an IC engine, how to make use of toluene lift thermometry, which was a single laser line excitation and then a two-color detection. So it's clear, I think, that the temperature, especially in engines, is very important. Why that? The temperature determines the rate of evaporation in case of, let's say, liquid injection, direct injection. It influences the mixture preparation, as I said, the ignition, eventually as well the auto ignition, later on the combustion process, and by that as well pollutant formation and heat loss. So it's very useful to have a tool that allows us to look into the temperature distribution, not only point-wise, but as well in a field. Of course, ideally later on in a volume, but that's something we cannot yet do. Later this week, we will discuss as well opportunities to do that volumetrically. If you're interested in more details, I refer you to a paper that we have published here in the Proceedings of the Combustion Institute. So, as mentioned, toluene LIF is a method where the emission band shown here for 4 different temperatures are shifted to the red side of the spectrum with increasing temperatures. These emission spectra are normalized, but you have to keep in mind that overall the intensity of the emission is decreasing for higher temperatures. And one of the primary reasons is, of course, you have a lower density and thereby less of molecules that radiate. So what we refer to is the two-color detection, maybe upon excitation at 266 nanometer. That is the 4th harmonic of a YAG laser, in many labs available, but some labs still have excimer lasers like krypton fluoride working at 248, which is as well a good tool for that. However, you do not necessarily to do it with a two-color detection. In principle, another strategy would be as well that you just take one camera with a filter somewhere here at 280 nanometers to get rid of photons that are scattered from the laser, and then just take one band over here. Of course, when the temperature changes, then the content of the emission in this spectral band will change, and in principle it can be used. Any idea why that is not a good choice? Where the problems could come from? It is, yeah.
Tracer density might change.
Say it again?
Tracer density might change.
The tracer density may change. That's one possibility. That is not only a function of the temperature, but if the tracer density changes for whatever reason, and this is not recognized, then the intensity will maybe change as well. And you interpret that as a temperature change, but in reality, it's just a seating problem. Yeah? And you will later on see as well other reasons why a two-color detection is beneficial, because you're taking a ratio. And then if the tracer density changes or the laser intensity changes locally, then by ratioing, that cancels out. That's why it is more robust against changes in your experiment which are difficult to control or naturally occur. So people have done that for quite some while, and here you see some references. I would like to refer here to a work by John Deck in the Sandia National Labs from 2009, where for low repetition rates, that was 1 shot per laser cycle, he was able to look for temperature stratifications. So very interesting to see prior to combustion, where you have had hot zones and cold zones, and here you see the delta T, the relative temperature changes that change locally, and of course depending on the crank angle and from cycle to cycle. However, for many questions it is useful to have that measurement done at high speed, meaning that during one cycle you can get more than one temperature map, and eventually to combine that maybe with PIV, because these multi-parameter measurements might give much more information about the transport than only the temperature field. And so the temporal evolution of a 2D field is something that can be useful to understand what's going on in principle. And I will show you here the application, how it's done, and the interpretation for specific problems I leave out. So the setup is shown over here. That is a cross-section through the engine with 4 valves. You see here the area where the light sheet has been placed. It came from the bottom through the optically transparent piston and was then shooting just against the cylinder head. And it was slightly off-center, and to give it some dimensions, 25 by 30 millimeters. And that was actually a 266 nanometer YAG laser, the 4th harmonic of a YAG laser. And because working at high speed, meaning 6,000 pulses per second, this laser was able only to provide 1 millijoule. And that's not too much, and that's why as well this experiment has been conducted not with air, but with nitrogen. So this was not fired, but it was just a motored engine, and to prove the concept and as well to show some features on an optical engine to be shown. And this is here the central tumble plane, and the observation then was through the liner, maybe better shown over here. It's not in this direction, of course, perpendicular to that plane. Here would be the cameras equipped with a filter for looking for the red part of the spectrum and the blue part, with this filter combination. But basically what it's looking after, one camera looks for the blue band and the other one looks for the red band. Okay, and overall that has been as well superimposed to 2D PIV that has been done simultaneously with a different laser at 532 nanometer, and that's why we have a 3rd high-speed camera located over there. Okay, so here are images that you would see at the different camera channels. A red image. You see here, this is just the pixels, and the color coding are counts. That's a recognized intensity. It's just a lookup table. And any idea why you have higher intensities here than here? After the toluene has been seeded into the intake. So somewhere here you have a nitrogen, and there is, let's say, 2.5% by volume toluene. This is homogeneously prepared. So the whole engine is flooded homogeneously with nitrogen containing some of the toluene.
This is before top dead center?
That is before top dead center, but yeah, it's before top dead center, I guess. But it's not so important whether or not, because there's no combustion. There's no combustion, and the toluene will not decompose significantly, even if you go through the cycle. You excite that with a laser coming from the bottom. The laser direction is here. Is that working? No. This is absorption. Yeah, this is absorption. In this direction, it's heavy, isn't it? And in this direction, that's the laser light sheet. It's not homogeneous. And that's why you have here a higher intensity. Due to absorption, it's getting lower. And to the side, you have less fluorescence because there's less laser intensity. The same holds true for the blue image. And if you would now collect the data only, let's say, with one band, let's say just add them up from the one band, then you would need to correct for the absorption, and you would need to correct for the laser intensity profile. If you now take the ratio, divide red by blue, you end up with this image where all these absorption effects and these intensity profile effects have been cancelled out. Of course, you need to match those cameras exactly on top of each other. Like in PIV, you use the same procedure, a calibration target and so on, that you know exactly which pixel in the red and the blue corresponds to each other. Only then you can expect that you have a cancelling of these effects of absorption, laser fluence, and eventually mixture inhomogeneities. Because it's maybe in other applications where you do not do the pre-mixing of nitrogen and air somewhere here, that you know it's homogeneous. Very often, for example, when you do toluene into the fuel, for example, You have inhomogeneities in the mixing, and then these would be canceling out as well if you take the ratio, not if you take a single band. Okay, then you see here our regions close to the cylinder head as well, not too far from the piston. The operation conditions were here that we have had 330 K for the cylinder head, and at least I would expect in this areas over here thermal boundary layers, because by compression eventually the gas mixture gets hotter than 330 Kelvin, and then you would have a gradient over here, and of course it would be nice to see whether we can detect it with this technique. So the crank angle here is 360, meaning at top dead center. So such an image where you now see the temperature given in this region of interest with this color coding here between 300 and 550 Kelvin has been obtained after some filtering, some median filtering, some binning to reduce the noise, such that in the end we have had something like 80 microns per pixel, which is not bad, but still you see some noise. Yeah, here are structures which are due to the lookup table are hotter than the neighboring ones, and that's unphysical. This is amplifier noise. I go back to the spectrum. We have the fluorescence both for blue and red in the UV, and that's why you have to use here in front of these CMOS cameras image intensifiers. And those image intensifiers we have used for that are two-stage image intensifiers, and they are noisy. And that is something you have to live with. Yeah, that is remaining noise. Okay, more details. Here, as already mentioned, the mixture preparation between nitrogen and toluene. The good thing about toluene is you do not need as much as other traces. It does have a very high quantum yield, such that you do not lose too much of the photons by collisions when there is no oxygen. And that's why here actually nitrogen has been used. You see here some more intake pressure and temperature conditions. Compression ratio, I already mentioned earlier this week, in this engine is 8.5. And what you see here as well is that the motored engine with the top dead center at 360 crank angle degrees shows here the pressure trace that is monitored. Somewhere here is the pressure transducer. And then that is well known in the engine community. You can, from the pressure trace, at least for the whole bulk, you can deduce the so-called polytropic temperature. This is nothing else than based on an equation of state, where, which is used to estimate now the mean temperature in the bulk of this cylinder load. And so very important as well is to note when the temperature due to compression is increasing, the lift signal overall decreases. So already from such a graph you can expect that your precision, your noise, is getting worse for higher temperatures later in the compression stroke. That is something you have to live with. Yeah? So the precision is not a constant over the whole cycle. A closer look into that, how can we now calibrate the system? As I said, this kind of thermometry needs calibration. And one possibility to calibrate is to use the engine itself in connection with the pressure trace and the polytropic temperature deduced from that. And then use a certain area somewhere where you are sure that you do not have any heat transfer to the cylinder head or the piston. So let's take this region over here. This spans 5 by 5 millimeters. And then you can, from this region, get a mean ratio from your toluene lift by this two-line ratioing, which is shown as this line over here. This is the lift ratio over the crank angle, and here you have the temperature as deduced from the pressure trace. And with that, you have a certain correspondence between the temperature deduced from the pressure trace and your spectroscopic method. And of course, that comes along with some noise. So if you motor that engine as well, you do have a certain variation from cycle to cycle. That is, but the smaller influence, the larger the influence is from the noise you have here in your camera images. And the precision uncertainty, to give you some numbers, around 3 Kelvin, we have a precision uncertainty of 5 Kelvin, corresponding to roughly 2%. If you go for higher temperatures, the absolute value goes up to 30 Kelvin in that experiment and a bit more than 5% precision uncertainty. So that might be okay for some questions. If you're interested in autoignition, it might be not good enough. Yeah, autoignition depends heavily, non-linearly, on the temperature, and already 10 Kelvin make a huge difference at 600 Kelvin. So it gives you an estimate, and for some questions, as I said, it might be okay, for others not. You can relax your spatial resolution. This was done here in a 3x3 binning region. If you're not interested in the smaller structures, maybe you release your spatial resolution and bin 10 by 10, and thereby you can improve your precision uncertainty maybe from 30 to 20 Kelvin. It's not a huge jump, but at least it's a bit better. Yeah? And so this shows you as well that for most of these spectroscopic techniques, you have a trade-off between spatial resolution and precision uncertainty. If you have a high spatial resolution, you collect less signal and your precision uncertainty shoots up. It's getting worse, and vice versa. A question, please.
So what does binning operation mean?
The binning operation means that you sample, you average your signal from a larger area from a larger number of pixels. Let's say you have, in the end, you have here from your CCD camera or CMOS camera, these different pixels shown here. And binning means that you now simply take the average of, let's say, 3x3 binning of these 9 pixels. Yeah? If you now have a larger binning area, then you collect you average the information from a larger area, and thereby your noise goes down. Because the noise is something which is uncorrelated between pixels, and due to averaging, then the noise decreases if it's ideally a Gaussian distribution of noise. Yeah.
Though this is based on the assumption that you have uniform temperature.
This is based on the assumption that I have uniform temperature. Correct. This is only to show what precision you can expect. And this presumes that you do not have any temperature gradient in this region where you perform your calibration from. Yeah? If you would place that location close to the cylinder head, that's not as wise because you presumably have heat losses depending on the crank angle to the wall. Okay. Then let's have a look into the results. If you go for the compression stroke, you see here for 300 Kelvin, meaning 300 crank angle, 60 crank angle before top dead center. If you take the average of that, this is around 390. You can follow that up now later in the cycle, 320, 340, up to the top dead center at 360, where you have then for this compression ratio, for this intake conditions, a mean average, a mean temperature of 532 Kelvin. Actually, I was a bit disappointed because the cylinder head is at 330. The technique is not resolving sufficiently such that there is no thermal boundary layer easily to be seen. Yeah, there must be one, but yeah, well, the technique has its limitations. Then the bit more interesting part starts if we go into the expansion, and remember it's motored, there's only nitrogen, it's no spark, no combustion. What happens then at 390, at 410? Yeah, something interesting happens, and that is maybe interesting for those of you working with optical engines, because you have a large crevice between the piston and the cylinder liner, because your piston rings are far away from the top of the piston. There's a large volume, and if the piston is going now down, you have an outgassing of these gases from these crevices. And because they have been trapped between cylinder and piston, they are of course much colder. And these cold gases come out now when the piston moves down. And if you look at these temperature distributions over here, they're up to 50 Kelvin colder. And this means that an optical engine late in the expansion stroke is not a good system to be compared with real engines. For example, for the formation of pollutants like NO, you will have an influence of these outgassing gases from these crevices. And that is more clearly visualized if you now take the distribution functions for the compression. For example, let's take an example at 360 here. For example, we have the top dead center. This PDF shows the distribution you will find in this field of view for the different temperatures, spanning around this 532 Kelvin as a mean value, but it looks more or less Gaussian. Yeah, so that is a distribution which appears rather symmetric at a compression. In the expansion, things become different. Let's take this 410 crank angle, meaning we are now 50 crank angle after top dead center. And there you see you have a skewed bimodal distribution with a peak over here and here. And that can be as well linked to a certain region. And that is shown over here to give some idea, just a second, about post-processing, what you can do. For example, to visualize what's done in the compression, you have here your more or less symmetric distribution. You can try to fit a Gaussian distribution to that. You have a reasonable fit. Then based on that outcome, you say, well, let's do the same for the crank angle in the expansion stroke. You fit it only with the right-hand side. You end up with something like that. And then you take the difference between the actual PDF and the Gaussian fit, and you end up with this blue curve over here. And then you backtrace where it comes from, and then you can, based on such a PDF and such a threshold, you can now identify a border of your cold gases. And that is a clear indication, yeah, they come somewhere from, and we know the crevice is just below. It comes from the crevices, quite obviously. You have had a question, please.
Have you ever tried to correlate that with hydrocarbon emissions
in the fired engine? We haven't done that because with the 1 millijoule in the excitation laser, we would not be able to detect anything useful. Because with the oxygen that is needed for the combustion, the signal levels would have been roughly a factor of 50, 80 lower, and then the signal to noise would have been very bad.
Even if you take this setup as it is and you just look actually at the
Okay.
cold nitrogen coming out of the crevice, I mean that's where most of the hydrocarbons emissions are coming from. Can you actually see then from different piston designs if that correlates with hydrocarbon if you then fired and measure hydrocarbons?
Yeah. The question is whether this is correlating with the hydrocarbons emissions. So the question actually traces back to the problem: the larger the crevice volume, is it really the fact that you have a larger hydrocarbon emission? That has not been done by us, but people have looked at that, and it's a clear correlation. Yeah. It's a clear correlation, and that is something which is very difficult to prevent. In an optical engine, depending on the optical excess, the height of the optical excess of the liner, you have to put back your piston rings because you want to avoid that the piston rings comes over a transition from metal to quartz. Yeah, and to prevent that, or you have to think of a completely different design. Maybe you make a very rigid, complete quartz liner, and all the piston rings. Not made from metal, of course, are going along that. It's, in principle, you can think of something like that, but it's not the usual way. So that's why these optical engines, I think, are good for, of course, motored conditions, to understand the turbulence, mixing, and so on. And they are good for looking for combustion not too late in the cycle, in the end. Yeah, because then you have at least to consider these effects. Okay. Of course, you can do now some statistics. Okay, there's another question, please. Previous slide.
So for the cold and hot gases, is this method universal or is defined by yourself?
The question is for the cold and hot areas here, whether this method is universal or self-defined. Yes. That is something that we have thought out on our own. It's not universal in that sense. Of course, it can be used in different environments where you have similar phenomena, but I think that is where, even if you have done good diagnostics, you need even more time to think about the post-processing and what to do with the data. Of course, you should do your experiment initially as well with a clear question in mind. Without that, it's, I would say, completely useless. But even then, if you have done that properly and you have a good question that you want to answer, you have a good experimental setup, then the real work starts to extract the information out of these terabytes of data. Yeah, you want to reduce it in the end to something like 1 or 2 graphs, and that needs some creativity, and image post-processing is part of that. And here, yeah, well, playing around with the data, of course, you have ideas, you test out ideas, and that is not the result, let's say, of an afternoon, but it's a result of many different options to look at the data. And that is, yeah, one possibility to at least visualize these lines. Because initially I was interested in heat transfer between these two things. In the end, it didn't work out. Our data was too noisy. But for that, we needed this clear distinction between hot and cold. And just drawing something like, in such a graph, a gradient, you're lost. Yeah? If you would have a clear hot and clear cold area, then you could look for the gradients and look for the Kenny edge filter, for example, and draw a line to distinguish hot and cold. But that is, the contrast is not good enough. There's too much noise. And that's why doing it like that way seemed to be the better way. The next step, as I said, unfortunately failed. My original aim was then here to look for turbulent heat transport. Okay. Here are some statistics. Now you can repeat that experiment for many cycles, and then look for spatial PDFs, looking for areas where you have a higher probability to monitor cold mixtures for different crank angles. And maybe again, the most interesting part is only here, where you are late in the cycle, after top dead center, where statistically as well you see the same phenomenon, regions of colder gases. Yeah, and that if you use such a technique now in another engine, maybe an engine where you're interested in auto ignition, HCCI engines, for example, that could be used eventually to see where you have, let's say, hot areas, or the probability for hot areas, and then as well probability for zones of auto ignition. That was as well an intention to develop a tool for this HCCI combustion. Combining that with PIV provides more insight, because based on the analysis I've shown, you can see here the demarcation of, to the left, the hot, to the right, the cold gases, and then overlaid is the PIV information that has been as well taken with high speed. And just to give some impression what that can be used or done with that, originally, as said, I wanted to study the turbulent transport, but doing such experiment now, time resolved, you see how this hot zone is transported during the cycle. Yeah, I've shown only snapshots here. Now see the movie. Yeah, it's repeated. Okay. With that, I think it has been shown that Toluene lift can be done at high speed, but in that case only in the engine environment because of the low. Just a second. Because of the low pulse energy in conjunction with nitrogen, where no combustion takes place. The two-color detection is beneficial because you can correct intrinsically the absorption and laser fluence effects, as well as eventually not perfectly mixed gases. The precision uncertainty is okay, between 3 and 6%. I would say it's quantitative. But for auto ignition, it's not quantitative enough. Yeah. For the motor engine, the compression stroke was more or less giving rise to more or less homogeneous distributions of the temperature. We could not identify the thermal boundary layers. And in the expansion, it was quite nice to see that we have cold gases coming from these crevices. You've had a question now. No, there was no question. Here's the question.
So the calibration that you said you did with the polytropic temperature, is there a reason why you didn't do it with the thermocouple?
The question is about the calibration. Why not using a thermocouple? First of all, it's not easy to place a thermocouple in that engine where you have no influence from the boundaries. So that would mean that the thermocouple has to be pointed somewhere in the center of the cylinder. That is, first thing is not easy. It's anyhow you measure the pressure trace, and this pressure trace has been used for decades to get a mean bulk temperature within the cylinder. So this is a well accepted method, and as well the temporal response of your pressure transducer is much better than a thermocouple. To have a thermocouple with a fast response time, you would need something like 100 microns or 50 microns thermocouple, and there's no fun. Yeah, and it's actually not easy to put it there. Okay. No further questions? Then maybe we can make an overall summary of this gas thermometry methods. So I think overall you can say this spectroscopy provides useful ways to measure gas temperatures without changing or obstructing the gas too much. We have seen that only cars is really non-intrusive. The others are, I would say, more minimal intrusive. You can receive a very good temporal resolution, whereas the spatial resolution, depending on the technique, is for high Reynolds numbers often not good enough to resolve the finest scales. More on, you cannot say that there is one method which is best. So using cars, although it seems to be the most precise and accurate technique, it is not easily applicable in all environments. And sometimes you're really interested more in a distribution in a field and less in a very accurate and precise point information. And that's why there are other techniques providing this higher dimensionality and therefore are preferable. Of course, you need optical access, and that can be a problem. Depends really on the combustor you're looking at, especially when you go for high pressures. And as well, the instrumental effort is rather high, and therefore you need expert knowledge. And I would say that is as well the primary reason why this kind of thermometry in industry is not as well spread or accepted compared to PIV. PIV you'll find in many companies in R&D, whereas this kind of thermometry, it's maybe only a few companies doing that. Okay. Are there any questions? Yes, please.
What is the spatial resolution in those measurements?
What is the spatial resolution in these measurements? I cannot give a general answer because that really depends on the technique and the application of your technique. In cars, we have had this something like...
No, I mean specifically for the toluene.
Oh, for the toluene, sorry. That brings me back. We have decided for 3x3 binning, having then acceptable noise, and this corresponded to 250 microns in plane, and out of plane the thickness of the light sheet was as well in the order of 200 to 300 microns. So you have had something like a cube 250 by 250 by 250 microns. Okay. Then we can finalize this chapter, or close that chapter, and continue with another topic, which is surface thermometry. And that is a technique which is based on thermographic phosphorus. And actually, I came across that technique when I had a visit in Lund University with Markus Alden, who was among the first bringing that technique to the combustion community. It has been used before, and you will see it's a very beautiful and actually very robust technique that allows us to measure surface temperatures in combustion applications, which are really harsh. And if time allows, I have some examples in this lecture, but if time allows on Friday, I can provide maybe as well some more information. So here's the outline of this chapter. I will have a brief introduction and motivation. We will then have a closer look into the most popular ways to exploit that process called decay time method or ratio method. And here we will see how they compare in terms of precision and accuracy. Then I will have a rather lengthy discussion of the error treatment to give you, at least for this one example, the effort that one should make to better understand what are the limitations of this technique, and then I will provide some application examples. So surface temperature, of course, are really important to know for many applications, not only for combustion. That's why we find different options how to measure them. Thermocouples maybe are among the most often used systems. However, they are invasive in a certain sense. You have to bring them to the surface. You have to drill a hole where you stick in your thermocouple, and then the sensitive part of that should be as close to the surface as possible. Possibly your wall material has a different heat conductivity than your thermocouple itself, and thereby I call that invasive. It is limited in its spatial and temporal resolution. Why that? Because you have a thermal inertia of this thermocouple, and to be really fast, and you need a very thin thermocouple, which is not easy to handle. Moreover, if you would like to measure, for example, the surface temperature of a turbine blade or of a valve in an engine which is moving, then it's not so easy to install a thermocouple into these moving components. That's why maybe pyrometry is the better choice, meaning infrared thermometry. You just use the naturally occurring emission of a hot surface. This is a technique which is very powerful in principle, but making absolute temperature readings out of that is difficult, because you must know the emission coefficient. And not all the bodies you're interested in are black bodies. They're gray bodies, and the emissivity might change as well. So how to deal with that? So relative temperature distributions, okay, but absolute, difficult. And in combustion, you typically have chemoluminescence. You do have soot radiation, and that's why pyrometry is sensitive against this kind of additional light which is generated in the combustion system. So that's why pyrometry can be of use for surface thermometry, but generally is difficult to apply because of that. What about temperature-sensitive paints or thermoliquid crystals? Those are not applicable for the temperatures we are interested in. They are not stable. People have regularly used in gas turbine industry, for example, heat-sensitive paints. These are paints that are brought into the gas turbine combustor or the turbine blades, and then you operate the system, and afterwards you have to destall that and look for the color change, and then you can see what was the maximum temperature the component has been exposed to. That's why you have no temporal resolution. So all of that is not ideal. And that is why the combustion community took over Thermographic Phosphorus, which are working on a very different principle. So these phosphors allow a broad range of temperatures to be studied. From cryogenic temperatures, you have phosphorus being sensitive from a few Kelvin up to something like 1800 Kelvin. They're insensitive against black body radiation. You will see they provide the information in spectral bands which are rather narrow, such that you can filter them off from the surrounding stray light, chemoluminescence light, and thermal background. And they provide good spatial resolution and as well a reasonable temporal resolution, which is typically good enough such that the temperature change of a surface is not as rapid as in the gas phase, of course, because you have the heat capacity, which makes it not so strongly varying in time, such that the temporal resolution very often is as well good enough to follow temperature changes. And you will see you can apply it as well two-dimensionally. It's not only point-wise measurement technique like thermocouples, like the potential from pyrometry, you have the opportunity as well to measure temperature fields of a surface. What are these thermographic phosphorus? So first of all, these are ceramic materials. And these ceramic materials are doped with either transition metals or rare earth metals. So you can think the ceramic material being a host material where possibly in the order of 1 to a few volume percent, you have in this host then these rare earth or transition metal ions. Yeah, they are then placed in this material, and actually what you do is you excite then these ions, these rare earths or transition metals, which are implemented in this ceramics, and then they have, of course, after excitation, they will emit light. It's like fluorescence, but it's in phosphorescence. It's a process which is, we call that spin forbidden. It's actually a forbidden transition in quantum mechanics, meaning that it takes longer that this transition happens. But it's like fluorescence, but it just on a longer time scale. And this phosphorescence shows a sensitivity with regard to temperature. So what you do, you exploit the spectroscopic properties of these materials upon electronic excitation. And the principle is rather simple. You just you select a certain thermographic phosphor, and you coat the surface with that. Well, I say simple. Actually, that is a practical step which is important and not so easy. The question is, how do you do the coating? If you would be a material scientist, maybe you would have sophisticated ways to do that. In engineering, what people mostly do is they use this phosphorus as a powder. Maybe this is milled to a micrometer or so. They put it into something like a binder, and then you do a spray coating. And then a spray coating should be as thick as needed to get a good signal. But keep in mind, you have a coating. And a coating means you're not non-intrusive, because now you have a material in top of your wall which typically does have different heat conductivity properties. And thereby it acts as an insulator because it's a ceramic. So you must keep that into consideration if you have a strong temporal variation of your surface temperature. So it's not non-intrusive, it is, let's say, semi-intrusive. Once you have that coating, you excite the phosphor by a UV light source, typically a laser, and then you detect the phosphorescence emission with a detector like a photomultiplier, or if you do it 2D, with a CMOS camera. You can do that in different ways. The most popular are time-resolved, where you have a fixed spectral range and take the temporal decay of that phosphor, or you do it time-integrated and spectrally resolved, meaning that you fix your temporal range, maybe directly after excitation, and then look for the spectrum. To better explain that, it's shown over here for a certain phosphor. It doesn't matter now which one that is. In the time-resolved way, you have somewhere here your laser excitation. If available, you just take a UV laser like a frequency quadrupled YAG laser, 266 nanometer, for example. And then you see over time that laser is over after 5 nanoseconds. This is here a time scale of a few hundred microseconds. So the laser is gone directly after in this time scale. And then you look for the phosphorescence decay after one shot of excitation. And you see here for this phosphor different temperatures spanning over 20 Kelvin only. This waveform is very strongly decaying with increasing temperature. And this waveform characteristics, the faster decay, is the information you exploit in this way for thermometry. You can now get for each of these decays a decay constant, and the decay constant after calibration denotes the temperature. The other way is to do it for a fixed temporal range. So let's say you take now your data after, let's say, 150 microseconds or so in a certain range. You integrate all the signals after that excitation and then spectrally disperse that in a spectrometer or using 2 cameras with filters looking for these 2 bands. Some of the phosphors actually show a behavior where the spectrum is changing with temperature. So here's wavelength, normalized intensity, and temperature. And for example, take 400 Kelvin, then this first band over here would be small against that band over here at higher wavelengths. And the ratio between these 2 bands is changing with temperature. At 800 Kelvin, for example, they are more or similar in size. So the ratio of bands can be as well used. Now you can more generally classify that. So you distinguish in a more general way time-resolved and time-integrated approaches. and we will go through them in a second. The time resolved can be split into a time domain and frequency domain. So the first is the decay time. That's just what we have seen before. Upon excitation, you look for the decay, and eventually you try to fit a mono-exponential decay characteristics to it. And once you've done that in a fit over here, then you receive this decay constant, tau, and this, after calibration, is a measure of the temperature. That will be exemplified further on. However, people as well have looked for phosphorus, where you have a certain increase upon excitation, which is again like a delta function. The intensity first increases before it decreases, and you can use this rising edge as well and fit an exponential function to that. Not as popular, but some phosphorus are good for that as well. Or you do it in the frequency domain. Instead of having a short laser pulse, you take a continuous laser or an LED lamp, for example, and then you modulate the amplitude. And the modulation of the amplitude of your excitation is this solid line over here. And because of the decay characteristics of your phosphor, the detector will see as well a modulated signal, a modulated phosphorescence, but there's a phase delay. And this phase delay is independent of the frequency of excitation, as well dependent on the decay constant. And again, the decay constant here is the measure of the temperature. That is as well a very robust technique when your time resolution needs are not as high, because you should estimate this phase lag not only from one period, but maybe from 100 or 1,000 periods. And let's say if your modulation is at 50 hertz, then 1,000 periods means, of course, many seconds.
Okay. So it's a fixed time delay rather than a fixed phase delay.
Yeah, it is. But what you see, it's of course as well. You can if you transfer that from the time into the angle, then I call this a phase.
Okay.
Yeah.
But what physically happens is a time delay.
What physically happens is a time delay. That's correct. Let's have a look into the other branch, time integrated methods. One possibility is you just take the integrated intensity. Yeah? Upon excitation, we have seen the phosphorescence decays. And if you have higher temperatures, it decays faster, so the integrated intensity will be less. So that's a possibility, but again, it is very sensitive against any changes in your setup which are not often controlled. For example, your phosphorescence coating degrades and you have less phosphorescence in total. Then you might interpret these loss of intensity like higher temperatures, but in reality, just your phosphorescence has degraded. Or you have less pulse energy in your laser as well. Lower intensity in the integral that you misinterpreted as higher temperatures. So that's not really recommended. Line shift. Some phosphors show line shift of their emission band, such that this line shift is as well, in principle, for some phosphors useful for thermometry, or the two spectral band. Some phosphors emit not only at one band, but at two or more bands, and then you choose certain areas, spectral areas, where you integrate the intensity from this band and from this band, and then you take the ratio, and this ratio is temperature dependent. And actually these two, the decay time and the two spectral bands, that is the most popular techniques that have been used. And it's maybe good to have a closer look into them. What are the pros and cons? So the motivation is for you guys, because that's really a technique that can be easily adapted to provide a decision support. What is, as I said, the pros and cons of these techniques? And this includes then to investigate sensitivities and have a closer look into precision and accuracy in the possible applications. And the procedure is as follows. That is done with using two detectors. Actually, these are two CMOS high-speed cameras. And from this data set, this identical data set will be used to evaluate the decay time method and the two-line method. Yeah, having exactly the same data, the differences cannot be traced to, let's say, differences in your experiment, because it's the identical experiment that has been used to evaluate with the decay time and the ratio. And that is exemplified here for one phosphor. This is the host material is this manganese fluor germanium oxide with this dopant Mn. Mangan in German, I don't know the English word for that, sorry for that. Manganese, okay. Okay, this phosphor as well shows two emission bands which can be used for this ratioing. And the experimental setup is as follows. There's a tube furnace, a large system where we have in the center, we know there's a homogeneous temperature distribution. There we place a surface, a substrate, which is coated with this phosphor. And in the surrounding, you have a target. Why that? We have to match the cameras looking for the phosphorescence. Again, like in PIV, we have to know the corresponding pixels. We have here a thermocouple. This is our reference thermometer. So we know everything is in equilibrium as well in terms of radiation. So the reading of the thermocouple is actually providing access to the temperature of this surface. Then we have these two cameras equipped, each with an interference filter. It becomes clear in a second which wavelength. These are corresponding then. One filter is looking for that part of the spectrum, the other for that part of the spectrum. But both of them looking as well not only for the spectral part, but as well CMOS cameras, high speed. They look for the decay of the two bands. Then we have a YAG laser to excite that in the UV. And very important is that here we have a beam homogenizer, because we want to have here at the surface more or less a top hat intensity profile. You will see later on in this lecture there is a certain intensity dependency, and that's why you want to have everywhere the same energy. And here we have another equipment, a polarizer and a half-wave plate. Some of you might know, if you now have here this half-wave plate, you can turn the polarization, and by that the transmitted energy is adjustable. And that's the best way to change the energy of the YAG laser. Don't do it with a current or voltage, yeah? Or with a Q-switch delay, for example, because then you change the beam properties. Keep the beam properties identical and better change the energy with this half-wave plate. Although it costs a couple of $1,000s, that's for sure the more reliable way. Then you see a photograph, not from the CMOS, but a digital photograph. You have here the target, which is used to calibrate or match the cameras. And here in the center, you have the phosphorescence. Yeah, data evaluation. First of all, the CMOS chips are nonlinear, so you need to correct for that. Then later in this lecture, I show this nonlinearity in more detail. Then you have to match these images that was used with the commercial software using the so-called pinhole model. The idea is really that you have know which pixel corresponds from one camera to the next. Then you have to somehow fit the lifetime, and the idea is to use a mono exponential model, and that is done here with a certain way. In the end, you can use as well a Levenberg-Marquardt procedure. In the end, you try to fit this mono exponential function to your measured waveform. And in that way, we do that here. There's as well some information about we do it that is not fixed in a certain time frame, but it's relative, or it's dependent on the decay time itself. So for the moment, it's not so important. That's why I want to leave out the detail. So in the end, you make a pixel-wise fitting of this decaying waveform. And then very precisely can estimate the decay time simply because you have, because of the high temporal resolution, maybe 2,000 data points that are used for the fit. The intensity ratio is done as follows. Because of the two filters, you have the two bands from which you centered around 630 and 660 nanometers. You take the ratio of these integrated bands, and you do that either taking only one frame of the CMOS camera, which was operated at 50 kilohertz, corresponding to 20 microseconds. So one ratio is taken from the time interval 100 microseconds after excitation to 120, corresponding, as I said, to one frame. Or you take a bit more, 50 images, where you have then a longer integration time from which you take these integrals. Is that clear? Okay. So what do you get? Lifetime, shown in blue. Here you see the lifetime in a logarithmic scale over the linear temperature. You see that this phosphor, up to, let's say, 700 K, has a rather low sensitivity. So lifetime is not changing too strongly with temperature. But to or make the idea again, maybe here with this view graph clearer, what you do after the fit, you get a certain lifetime, let's say this lifetime, and then after this calibration, you know this corresponding temperature would be that one. If you have a certain imprecision of that, let's say you have the scattering in this area over here, then this sensitivity would translate that to a certain temperature insensitivity spreading over a certain temperature range. So the higher the sensitivity, the steeper the curve, the better it is. But of course, it comes along with a high dynamic range. If you're in the area with a strong slope, then your detector must be able to operate in a large dynamic range to measure these different time scales, yeah, or these different decay times. If you do that with 660 or 630 nanometers, okay, going back, that were these two cameras, this and this camera, they are providing independent information. Having a look on the lifetime, you see, independent of the spectral range, they are superimposing perfectly. So the decay time seems to be not dependent on the spectral position in your emission spectrum. The ratio is shown over here with one image, ratio 1, or average over 50 image, ratio 2. You see to the right-hand side, this is again the scale shown over there, over the linear temperature range. You see that independent on the ratioing, if you sample sufficient images, of course it doesn't matter, you see the sensitivity curve for the ratioing method. Okay. Now let's have a look at the precision. The first kind of precision you can look at is the shot-to-shot standard deviation. So what you do is you have your furnace, your oven at a fixed temperature, everything is homogeneous, everything is stable, and you just repeat your measurements. And then for each pixel, you can look at how this temperature information changes temporally. And that you do for, let's say, the inner part of your image, let's say, an area 15 by 15 pixels have been evaluated over here. And you do that for the lifetime method for different temperatures. So you repeat your experiment over a certain temperature range. And then you see the standard deviation in terms of the lifetime starts with something like 1%. That is the area where your curve was not very sensitive. And when you come to the very sensitive end of your calibration curve, this end over here, then you end up with a temporal standard deviation in the order of 1/1000. So it's very precise. Let's have a look for the ratio. If you have the ratio taking over only one image, it's worse than taking over 50 images. However, for increasing temperatures, the temporal standard deviation starting from something like 1% is going up to 10%. So that's already a first drawback you see from the ratio method, because you do not have a fit over many hundreds or ideally thousands of data points like in the lifetime. In the ratio, in the end, you have two quantities simply from integration that are divided by each other. So much worse. Here is a difference of 2 orders of magnitude. Let's have a look into the spatial noise. Because we are taking pictures, we are taking images, 2D distributions of the temperature. So as well, you can look for a pixel-to-pixel standard deviation. Ideally, you have a homogeneous temperature map measured. The temperature from which you take that, of course, is homogeneous. We know that. And so doing that, In the lifetime method, you start again from something like 1% in a range where your system is not so sensitive, and then you reach as well 1/1000 in a range where you're very sensitive. And the ratio method in all cases is much worse to get. So that is a huge difference in terms of precision. Let's have a look into accuracy. Accuracy means you have to evaluate systematic errors, and that's typically much more complicated. So you have to think of ways to do that. And here I will exemplify that for two temperatures. One temperature where the sensitivity of the lifetime method is low, and one temperature 780 where the sensitivity of the lifetime method is much higher. The sensitivity of the ratio method is not changing so drastically over the whole temperature range. And so the idea is now that we have a look what happens after calibration. What happens if you change the energy? Because typically that is happening, because you do not have a perfect flat profile in the intensity of the laser. Or you have changes in the optical excess, and locally the energy distribution changes. Or you do have, after calibration, changes in the optical settings. That as well is something that will happen in your experiment very often. Maybe your colleague touches the camera and doesn't tell you, he or she doesn't tell. And you will see that makes a huge, can have a huge impact. We start the discussion at 5:15. And what you see here, first of all, is an excitation energy change over something like 1.5 orders of magnitude. So the true value is given here by this dashed line. Here's the measured temperature, and this is the normalized temporal standard deviation. And so for the lifetime method, now I refer only to one spectral band, that has been as well reported earlier in the literature from us. You see that you need a certain, for this low sensitivity range, you need a certain minimum temperature such that you reach the true value. Actually, I've forgotten where we have done the calibration for which condition. So the idea was to have the calibration done first, and then coming in next day and have or doing it 1 hour later and do this energy scan. And the ratio method with 1 or 50 frames shows with 1 frame this behavior, and with 50 frames a constant offset. So that's not an exception, because something must have happened between the calibration and actually data taking. And the PhD really was careful about it. Something must have happened. Yeah? In the standard deviation, you see that the ratioing here is not too bad, but you have a constant offset. The constant offset means this is inaccurate. Let's have a look at the energy dependency for 780, where for the lifetime you're now in the really sensitive range. Here, the blue, the lifetime, is very, very accurate and very precise. And the ratio method is more dependent on the energy. Okay, so a huge difference. The difference becomes even more if you now make changes of the optical setup. Maybe it sounds silly to you for the first glance, but filter rotation makes a difference. Filters are not perfect homogeneously, and you just rotate them maybe by 30 degrees or so, or tilt them, and you find the lifetime method is not changing. So this is the index. Filter rotation means 1. Lifetime method is not impressed by it at all. The ratio method changes, 20 degrees K. It's a lot. Or you now increase the distance. You shift both cameras by 1 centimeter, 2 centimeter, or 4 centimeters. This is 2, 3, and 4. The lifetime method is not impressed at all, but the ratio is. So if you decided to use the ratio method and you've done the calibration, don't touch anything. Don't touch it. How do you do that? Difficult. So you have to recalibrate as well, not only every day. You have to recalibrate as often as possible, or what you should do is in the beginning, you do the calibration often and ensure that in between the calibration has not changed. When you know that typically after 2 hours still everything is okay, do it after 2 hours, not every 10 minutes. But initially check it more regularly before you maybe have an inaccuracy. Or changing of the camera angle as well has an impact on the ratio, but not on the lifetime method. And the same holds true. Don't ask me why it's now a positive change. At higher temperatures, the lifetime method is not impressed by it, but the ratio method is changing for these higher temperatures. I have no real idea why here it's negative, the change, and there it's positive. The important message is only it's changing, it's sensitive. Okay. Then let's have a look into a very simple application to demonstrate now some images, some outcomes as well, where you see the differences in noise. That was simply a stainless steel block shown over here, which was placed in the oven. And then the upper part of this stainless steel block was cooled by water. Here you see the stainless steel block was cut such that the cooling or the heat could go only through a very thin part of the metal, meaning there is a thermal resistance. That this part can be cooled and has lower temperatures than the lower part. And then again, the phosphor was coated over here, and there were some targets, spots to match the cameras. And so what you see now here is the lifetime method, with the color coding being the temperature, and the ratio 1 with 1 image integrated, and ratio 2 with 50 images. Already, although in the beginning everything was at the same temperature, the cooling device was not switched on, the spatial noise is clearly evident from the ratio method. And now I switch on the cooling. So over time, until we have stationary conditions at some stage, maybe I should stop it somehow. Then you find a cooler part here in the top and a hotter part down here. Again, you have much higher spatial noise, obviously simply by inspecting. Okay, now let's have a closer look into the last 16 frames and do some statistics out of that. Here now, they are turned now by 90 degrees. You see again here the lifetime, ratio 1, ratio 2. And that is now transferred by after vertical binning, and we have had the question binning means now here all lines are summed up together, and then you end up with a with an average for lifetime. That's the blue curve, much less noisy even after vertical binning compared to the ratio method, which still shows some noise. And if you now look into the normalized temporal standard deviation, in this case, the difference between the lifetime and the ratio method is not so high. However, if you go now into the normalized spatial standard deviation, as obvious from this inspecting these images, a lot of noise over here, much less noise over here. That is a huge difference. Yeah, it's below 1% in the lifetime, and it's in the order of 4% in the ratio method. I have to say, for this phosphor, for this excitation, for this camera, for these filters. However, I think it clearly shows that depending on how you do the evaluation, you have strong differences between precision and accuracy of these methods. And if doable, I really recommend to do it with the lifetime method. Not always that might be possible, but if, it seems to me the better choice. And the main result is for the range where you have really high sensitivity, the lifetime method is really superior, whereas in the low temperature range, at least the spatial standard deviation and the accuracy of the lifetime method is much better than the ratio method. I have to say that because our reviewers as well pointed to that point. Be careful because for other phosphorus it could be different, and that's what I'm claiming here. What I've shown here, these drastic changes, especially with regard to the precision, are really for this phosphor. You might find another phosphor where the ratio method is maybe behaving not as bad as here. So the message is you might investigate that for each phosphor individually. Okay, I think it's time for a break. After the break, I'm happy to take any questions, and of course then we will continue and have a closer look into the error treatment of the lifetime method. Thank you.